Dr. Bert Drake is a distinguished researcher and science communicator. He is internationally recognised for his work and public lectures about climate change. Dr. Drake's most notable research is his 20-year, I think one of his more notable, but research is a very long study, a 20-year study of the effects of elevated CO2 on a Chesapeake Bay wetland. It's now the longest running experiment of its type ever undertaken. In collaboration with NASA, the CO2 research was expanded in 1996 to include similar studies of a nutrient and water-limited dwarf oak forest on Merritt Island Wildlife Refuge at the Kennedy Space Centre. His long research record and his public outreach has been recognised by becoming designated a distinguished science lecturer at the Smithsonian Institution. With no more ado then, I wish to welcome Dr. Bert Drake.
Okay, well, it is really a privilege and an honor to be here in this terrific forum. I've had the advantage of seeing the results of all the speeches. I've seen some of them on webcast, and I've read all of them. And I must say that I was really impressed by the level of expertise that was brought here to talk about energy. And in looking at that, it occurred to me to wonder why in the world would you choose somebody from the only state that has failed to recognize the Kyoto Protocol, that is perhaps a greater polluter of greenhouse gases per capita than Australia, and which has a political system which is in utter denial that we have anything really to worry about. It's a strange selection, but I'm very delighted that you chose me to come here. And I'm not really going to talk about energy today, because it seems to me there's nothing to be added to the terrific speeches that have already been given. Throughout them, it was mentioned over and over again that we basically have three choices in confronting climate change and the energy crisis, because the two go together. The first is to commence a very serious program of improved efficiency and conservation. And there is enormous scope to improve things there. Maybe a 30% to perhaps 50% of the way we need to get to energy use that would reduce greenhouse gas emissions comes from conservation of one kind or another. The second approach would be to switch to energy which is renewable or which doesn't have carbon involved, and that would be nuclear energy. That's a very contentious word here. I realize it is, but an excellent talk was given. I think it was John Bartlett's talk on nuclear energy, and it had all the basic facts there. The science community is full square behind nuclear energy as something that we probably cannot do without, particularly when the safety issues or the health issues are stacked up against coal. And the third thing we can do, in addition to renewables, which would include nuclear, wind, and solar, and those are going to be big in Australia, is to decarbonize coal. You have enormous coal resources in Australia, and you export a great deal of it. It's a big component in your economic base, and it occupies about 70% of the greenhouse gas emissions that you put out. So you have tremendous scope there for improvement and for carbon capture and sequestration. That's a new technology, but it would make coal useful, and coal could then be used to make liquid fuels and so forth. So going forward in the future, it doesn't seem to me that there are really any limits to energy in Australia. The limits are really on the constraints that you must recognize having to do with the environment. And so today I'm going to talk about one aspect of that, and that is the importance of recognizing what we're doing to the biosphere as we raise greenhouse gases, we increase the warming, and the possibility that we will degrade one of the major sinks for carbon dioxide, namely the land plants. That's the subject. And the conclusion is going to be, that I'm going to try to support, is that we are on the way to really degrading that sink. And if we do, then the rate at which greenhouse gases are going to go up will be multiplied. And we don't know how quickly they will go up, but we know that they will go up much, much faster than they are now. So that's the agenda for this afternoon. On the way here, I visited Mauna Loa. Why in the world would you go there apart from the fact that it's warm and delightful and there are beautiful beaches? And the reason to go to Mauna Loa for me is a kind of a pilgrimage, because way up on the flanks of Mauna Loa, that's Mauna Loa, and we're at about 11,000 feet, is this cluster of buildings. Now, I drove there the day before I took this picture. You could only go 20 miles per hour on what is probably best described as a goat track through lava. This is a huge lava field. Mauna Loa turns out to be the biggest mountain mass in the world. And on the flanks is this cluster of little buildings. And this is what it looks like up close. In the 1950s, about 50 years ago, in fact, exactly 50 years ago, Charles Keeling set up an instrument in this little building, or what was the precursor of this little building, to measure the carbon dioxide concentration in the atmosphere. He was really the first one to do it, and he was sent to Mauna Loa because the measurements that he was making in California were unbelievable to anyone but him. Because what they showed is that the CO2 concentration in the atmosphere would go down in the summertime and up in the wintertime. And it didn't seem to matter where he went to make these measurements. Everybody tried to argue that it was the closeness to Los Angeles and so on and so forth. In any case, he was given enough money to come to Mauna Loa and set this instrument up. And he began making measurements, and it didn't take long for the science community to recognize that something really unusual was happening. When I was in graduate school forever ago and taking plant physiology, it was said the concentration of carbon dioxide in the atmosphere is about 310 parts per million. And it probably doesn't vary much from that. One of the reasons we said that was because we didn't have the tools to make really good measurements. And Keeling had the knack to be able to tune instruments and tinker with them. He was using one of the first really functional plant infrared gas analyzers. Incidentally, the very first one, as far as I know, was produced at the Smithsonian Institution in 1935, but that's another story. I went here to see where these measurements were made. I got to see the original instrument, which was only retired about 3 or 4 years ago, because it had tubes in it, not solid state. In any case, Keeling made his measurements, and he was recognized for it by the name of this curve, which is CO2 concentration in the atmosphere up here and year down here. This is the so-called Keeling curve, and you can't see very well, but it starts down here at about 315 parts per million, and that's 375 parts per million at the top. That little vial of gas that I'm holding was collected there that afternoon a week ago, and the concentration was 382.6 parts per million, which is off scale up here. Now that's about 67 parts per million more than it was when Keeling started his measurements. I started my experiments when the CO2 concentration was right about here. It's now 10% higher than when I started my experiments.